Hello, hello.
So the next speaker for this session is Malhar, and he will be talking on robust hypothesis testing with abstain.
Hello, everybody. Thank you. So this is joint work with my advisor Vinod and Sasthanand, who was a postdoc here earlier. So consider a binary hypothesis testing problem. So you are seeing n samples from some distribution, either from P0 or from P1, and you have some detector which takes these n samples and outputs 0 or 1. It tries to determine what distribution the samples came from. So this is a very classic thing. This has been very well studied. So what we want to consider is, what if there is some corruption, like the samples generating distribution, like whatever method you have for collecting the sample is not perfect. Not all of the samples are coming from P0 or P1. So we model this as adversarial corruption of samples. So I'll describe later exactly how this works, but some fraction of the samples will not be from the distribution. They will be corrupt, they'll be chosen by an adversary. And we give ourselves some more freedom in this model, which is that we prefer a system which doesn't commit to an action when something is wrong. So what we do is we will allow for abstention. We can also later consider the case without abstention, but we allow ourselves to abstain if we can detect that something has gone wrong. So specifically, so there are some related, I'll describe one. Okay, so there's a lot of work in nearby areas. So this is classification with abstention. The rejection option has been studied. There's also a lot of machine learning literature with reject option when you see out of distribution samples or stuff like that. And so there's some work in information theory on hypothesis testing with multiple hypothesis testing with reject option and so on. And yeah, so there's also, so robust statistics is a huge field where it is estimation task. You want to estimate the mean of some distribution or something like that when some fraction of the sample are corrupted. So so all these various things are there from which we are inspired. So these are the works which are closest to ours. So yeah, so you can check them out also if you want. So let us look at our model in detail. So when the adversary is present, the xn samples are generated, but they're given to the adversary, and it can corrupt them in certain manner, which I'll describe later, and it changes them to some samples yn, which then goes to the detector, and it can output either 0, 1, or abstain. And in this case, it is only an error if you detect wrongly. If it is H0 but you said 1, it is an error. If it's H1 but you said 0, then it is an error. But it is not an error to abstain. The other case is when the adversary is absent. In this case, the samples are just directly given to the detector. In this case, you should not abstain. Abstaining counts as an error. And you must detect the hypothesis correctly. So you must have, if it's 0, you must declare 0. And if it's H1, you must declare 1. So now let us look at the contamination model, how the adversary does this corruption. So for example, this one thing, adversary samples observes these uncorrupted samples, the entire vector, and nature chooses when the adversary gets to attack. So when for a corruption at level epsilon or with budget epsilon, nature will choose a vector which is IID epsilon, Bernoulli epsilon, probability of epsilon the adversary gets to attack. Then whenever the adversary gets a chance to attack, he can replace exercise with whatever he wants. And so this model is called the memoryless ingress contamination, we call it that. So because that when the adversary gets a chance to attack is memoryless, it is not is independent, so to speak. So we also consider two other models. One is fixed weight where nature chooses the samples, the locations of attack, but instead of being IID, it is a fixed, the weight of the attack vector is fixed to be n epsilon. And this other model is strong contamination, where the adversary gets to choose where to attack after seeing the xn samples also, but it is limited to a budget of epsilon. So this is really the interesting kind of model, but we also studied the other things. So in this talk, I'll focus on the memoryless ingress, but I think it is easier to explain. Yeah. No. So the adversary gets to see all of the symbols and all of the attack locations, and then it can choose which to replace with whatever. So this is an offline sort of model. Yeah. And again, so what are the error events? There are 4 types of error events. When the adversary is absent, declare abstaining or saying wrong things both count an error. And when the adversary is present, just incorrect hypothesis counts as an error. So these are the 4 error events. And corresponding to these events, we study the 4 error exponents. So all of these events as n tends to infinity will go down exponentially, but we want to study how fast they go down, and we want to study what sort of exponents are achievable. So this is a result for memoryless contamination. So so as long as these 3 conditions are satisfied, this quadruple is achievable. And so a word on this. So note that the trade-off between these 2 exponents, which are non-adversarial exponent, this is the first one. This is actually just the classical trade-off between these 2 exponents when there's no adversary. Like without contamination, without anything, the classic point versus point detection, this itself is a trade-off. And in addition, once you have this trade-off sorted off, you just have a trade-off between this and this one, and this and this one, but you don't have any other cross terms. Each one only. So each of the adversarial exponent is in opposition to just one of the exponent. So basically, we'll see this in the picture. So this is the detector that we use. So around a KL ball of some certain radius around P0, we declare 0. So KL ball means all these distributions have KL divergence at most lambda 1 per given 0. And similarly around KL ball around P1 we declare 1. And the point is that, and everywhere else we abstain. And the point is that when the distribution is P1 and there's no adversary, then basically this boundary. And there's no so when H1 is true and there's no adversary, 0 and abstain both count as an error, and 1 is what you want to declare. And on the other side, opposite to that is when the hypothesis is 0 and adversary is present, then 1 is an error and 0 and abstain are what you want to declare. So this boundary basically controls the trade-off between those 2 errors. And similarly, this boundary controls the trade-off between the other 2 errors. So these 2 boundaries will give you these 2 trade-offs. And this top one is basically just saying that these 2 balls should not intersect. So we will look at the converse first. So I'll just give you a quick proof sketch. So suppose you have some pair of exponents which the detector claims to have achieved. And so this means that around this KL ball, the detector must output 1. Otherwise, it is not really achieving this exponent. But now consider the following attack. The adversary just picks some distribution U, and whenever it gets a chance to attack, it will just attack with that distribution. So this is a very oblivious attack. It does not need to know the entire action vector and so on. So what this effectively does is the samples yn are generated, adversary is picking some point in this set, in this black oval, and the samples yn are generated IID according to that. And if a large deviation occurs from some Q star to P star, then that will cause an error. And the worst case large deviation, that is the minimum KL separation between these two sets, will give you the exponent of yeah. So yeah, so this basically, and similar condition is true for the region around 0. And I'll show you, yeah.
The best attack that the adversary has actually.
Yes, the best attack is actually objects. It does not. And so we want to achieve this pair of exponent now. So we look at achievability. And so basically we condition on how often the adversary gets to attack. So on average, it gets to corrupt epsilon fraction, but in any given instant, it might corrupt rho fraction. So this happens with some exponentially small probability, but we are dealing with exponents, so this is not negligible. So consider the case where it got to attack rho fraction of times, and look at the samples which were not attacked. Those samples are drawn from P0, but they might suffer a large deviation and actually look like some Q star. And if this Q star happens to be close to the region where we are declaring 1, then the adversary can choose some U to make it to sort of bridge the gap. So as long, so, and then you, and this is basically the only thing that can go wrong. And so what happens is that, yeah, and the probability of this kind of thing happening is that you are looking at just 1 minus rho fraction of the sample, the uncorrupted samples, and they should suffer a large deviation. Instead of looking like P0, they should look like Q star. So that is this exponent. So overall, the chance of this event happening is the product of these two. And if you minimize over rho and over the adversary's choice, this gives you the worst case exponent that can happen. So this gives you a different, so this gives you the achievability, but it turns out these two expressions are actually the same. So we can show that these two are the same. So that gives you a tight characterization of the. So I'll just quickly show you the result for the other ones also. So when instead of IID attack, the adversary gets to attack just a fixed number of times, it actually just it's actually just this expression, but instead of minimize, you don't get to minimize over rho, you have to attack epsilon fraction of time. So you just get this expression without this. So that is what this is. And for the strong contamination case, again, it is the same as before, but instead of this mixture of taking Q and U, you have a total variation ball, because before the adversary was just able to get a mixture of its samples and the distribution, but now it can see the realization of the xn samples and then choose its selector. Yeah, so this is so these are the so this is basically the trade-off region. You can pick any point inside this region and then read off the corresponding adversarials. So these are the non-adversarial exponent. This is the classic trade-off. It is the same for all three models. And then you can pick up any point under this curve and read off the corresponding exponent from this side. That gives you a curve. This describes the achievable. So let us look at just one of these graphs. So you have fixed one of the adversarial exponents, if you fix this lambda 0.1 to be 0.1, and we're looking at varying epsilon, look at the adversarial exponent. And we see that the fixed weight uniform ingress is the easiest model. That is where we achieve the highest exponent. And the other two models are not comparable. In some regions, one is easier, in other regions, the other one. And one last thing I want to say that abstaining actually does help. If we do the same thing, but don't allow the detector to abstain, then we achieve much worse things. So here we are looking at sort of Chernoff exponent thing. What we are saying is that just look at, you take all the 4 exponents and just look at the worst one and find me a detector that has the minimum value for, has the highest value for the smallest of the 4 exponents. And you compare this for the case with abstention and without abstention, you see that with abstention, you get a huge benefit. So of course, so that's all I have. So in conclusion, we want to have this abstain option to do this, and we consider these 3 contamination models, and we characterize the trade-off between the areas, and we see the benefit of that. So, yeah, thank you.
Are there any questions? Not, let's thank speaker.